We know that a magnetic field is produced by electric current or by a motion of charged particles. The magnetic field produced by a solenoid can be understood to be due to passage of electric current through it. Hence, the question arises as to how can a bar magnet without any apparent observable electric current produce a magnetic field? Now consider the following. A bar magnet is made up of atoms, and in these atoms a definite number of electrons move in various possible orbits. Such motion of electrons in orbits can be considered as an electric current around a closed path with magnetic dipole moment IA. I is equal to electric current and A is equal to area enclosed by the orbit. In addition, the electron has intrinsic magnetic dipole moment due to its property called spin. The magnetic dipole moment of an atom of any given element depends on the distribution of electrons in various orbits and on their spins. In short, each and every substance has some kind of current distribution due to the atomic electrons. If the current distribution happens to be such that it has zero magnetic moment, then such a substance will not act as a bar magnet. In general, magnets are made up of iron, and the atoms of iron, Fe, normally possess magnetic dipole moment. In spite of this, an ordinary piece of iron does not behave as a magnet. The same iron piece can be converted into a magnet if it is kept in a strong magnetic field for some time, and then the applied magnetic field is slowly reduced to zero. What happens is the following. When an iron piece is kept in a strong magnetic field, the elemental atomic currents get redistributed in the iron piece and do not return to the original current distribution on removal of the externally applied magnetic field. It is because of this that a bar magnet possesses magnetic field. The question can be further extended. How do we understand the fact that when a bar magnet is cut into two pieces, both of the pieces behave independently as magnets? To analyze this, let us try to see how a current-carrying solenoid behaves as a bar magnet. In reality, its turns are very close to one another, but for clarity only a few turns are shown, separated from one another. Each turn can be treated as a closed current loop, and hence a magnetic dipole moment can be associated with each turn. Thus, each turn can be treated as a tiny magnet with north and south poles. When we look normally at the plane formed by the closed current loop, if the current seems to flow in clockwise direction, the side of the loop towards the eye behaves as a south pole and the other side of the loop behaves as a north pole. Figure shows a circular current loop carrying current in clockwise direction. If we look at the plane in a direction normal to the plane, then the plane on the side of the eye acts as a south pole, while the plane on the other side behaves as a north pole. The symbolic S shown here indicates south pole side. Similarly, if the current seems to flow in anti-clockwise direction, then the side of the loop towards the eye will behave as a north pole and the opposite side will behave as a south pole. See the symbolic notation. In this context, now observe the solenoid as indicated. The current in the circuit in front of the eye is in the anti-clockwise direction. Therefore, the side of the first turn towards the eye behaves as a north pole, hence that end of the solenoid is indicated by N, while the other side of the turn is the south pole for that turn. For the second turn, the side towards the eye is again a north pole. Similar is the case for all the turns of the solenoid. The magnetic dipole moment of every turn is in the same direction, and hence the magnetic dipole moment of the solenoid is the vector sum of the dipole moments of all the turns. For current I through a solenoid with total number of turns N and with cross-sectional area A, the magnetic dipole moment of the solenoid is given by Ms is equal to Nia. Now let us go back to our question. A bar magnet of original length 2L divided into two equal parts. Also consider the two equal pieces of a solenoid with N turns. If we assume that the pole strength of a bar magnet is M, then its magnetic dipole moment according to definition is given by Mb is equal to 2ml by definition. Now each of the halved pieces has magnetic dipole moment. Mb by 2 is equal to ml. On the other hand, when we cut the solenoid in two equal pieces, one of the newly opened faces of the solenoid behaves as a north pole, while the other new face behaves as a south pole. As a result, both pieces of the solenoid behave as independent magnets. The similarity between a bar magnet and a solenoid raises the following question. How much is the pole strength of the solenoid? We can answer this by using the information gained from the bar magnet. Equation gives the magnetic dipole moment of the solenoid. Taking the help of equations, we can define the pole strength of the solenoid. Ms is equal to Ms by 2L is equal to Nia upon 2L, where 2L is equal to length of the solenoid. Therefore, Ms is equal to Nia, where N is equal to N upon 2L is equal to number of turns per unit length of the solenoid. Pole strength of solenoid is equal to number of turns per unit length into electric current into cross-sectional area of solenoid. The unit of pole strength is Am.